All right, this set of notes goes through lenses, which is an obvious application of bending of light or refraction that we've learned about earlier. Quick little review question. Looks very similar to what you did in the refraction inquiry, except we have a glass rectangle rather than prism. Question, which way will the light beam refract? All right, in order to look at this, we want to make sure we draw the normal line, right? This makes a 90-degree angle with the edge of the glass air interface. This right here is our angle of incidence, and as we learned, when air goes into glass, it slows down and it will bend towards the normal line, where this refracted angle here winds up being less than the incident angle. Upon exit of the glass, the light ray will then bend away from the normal line. So we have to draw our normal line again, and there you see that that beam comes out parallel basically to the original ray. It winds up being disjointed, as you guys saw in the refraction inquiry activity. Now when we look at lenses, we have two types. Okay, you once again have either concave or convex. You can remember concave, it caves inward. Vex is outward. Okay, you can look at it as many pieces of glass put together. So here we have a convex lens that's thick in the middle, thin at the edges. And notice the middle piece looks like a rectangle, little trapezoids, triangles, right? And we kind of went through each of these little portions here, right? If the light came in on this little triangular piece, if you drew the normal line there, it would bend down, and on the exit of the glass, it would also bend down. If I did this with the triangle reversed, right, then it would bend up, all right? Light that goes in along the normal line of a rectangular piece of glass would continue to go straight through. You could do the same operation here with these trapezoids, and you could show this come down, this one come up, and all this light would converge at a location also known as the focal point, just like with mirrors. Okay. The concave lens, on the other hand, that's thin in the middle and thick at the edges, will then diverge light. And if you backtrace all of these refracted light beams, they will appear to come from a location on the front side of the concave lens, also known as its focal point. Okay. So if we look at a convex lens ray diagram, it's going to share some similarities with mirrors, but there will be some slight differences. Okay. Once again, we have our principal axis that goes right through the middle of the lens. Okay. In this case, we are going to draw the focal point on the back side of the convex lens, because that's where light will be focused. But we're also going to put a symmetric one on the left-hand side, and you'll see why in a second, right? The reason we need them both there is because light actually goes through a lens to the other side. So we're going to make use of both. Right? Just for, point of reference, if this is the focal length, then this spot out here would be 2 times the focal length. Right? If we were to place an object down here, right, outside of 2 focal lengths away, all right, our first light ray we're going to draw is horizontal. And as we saw in your inquiry, this will refract downward and go through the focal point. Okay? Now, little error in this diagram, but we're not really going to worry about it too much. When the light enters the lens, it will start to bend down a little bit and bend down again when it exits. These lenses are so thin that we're not going to worry about it, even though our lens is drawn pretty thick in this diagram. We can just send the light ray in and show it coming, downward through the focal point. Our next light ray that we'll draw is through this symmetric focal point on the front side of the lens, and it will bend upward, right, and refract across horizontally. Now with lenses, if you ever send a light ray at the very center of the lens, it will continue straight through. And notice that all three of these will meet at the same exact location, and we wind up getting an image that's inverted. And in this case, it is a real image because light does go from one side of the lens to the other. So this is a little bit different than mirrors. Whenever we had images behind a mirror, they were virtual. For a lens, though, they will be real. Okay. This image does also happen to be a little bit smaller than the object, and we'll see that whenever we're more than 2 focal lengths away, the image will be a bit smaller than the actual object. Okay. Do the light ray trace again, move the object in a little bit, horizontal light ray, down and through the focal point, through the symmetric focal point, horizontally across, straight through the lens, keeps going through, and we once again get a real image on the back side of the lens. However, it is much larger, right? So as we move the object towards the focal point, the image gets further away as well as larger, kind of like you saw in the curved mirror lab before. Another situation here, if we bring the object inside of the focal point, our first light ray we will draw once again is horizontal. It will refract downward through the focal point. Now, this next light ray we have to draw as if it, this one is straight through, right? So at the center of the lens, it will continue straight. The third one we could draw is as if it came from the focal point, and that will refract horizontally. And notice that all three of these light rays are spreading out on the back side of the lens. They will never ever meet. If we back trace these refracted light rays, you will see that they all come from roughly the same location. That is why when you look in a convex lens at an object that is very close to it, you will see a very large upright image. Okay, so virtual, upright, and large. Now notice virtual images for a lens will appear on the front side of the lens, all right, because the light doesn't bounce backwards like it does off of a mirror. Another case here, this is kind of the special one, just like an object on the focal point of a concave mirror. When you have one for a convex lens at the focal point and you do your light ray traces, you'll get parallel light rays, which will not create an image neither real nor virtual. So if you wanted to use a convex lens as a magnifying glass, you would need to put it inside the focal point so that you got a larger upright image. If you wanted to use a convex lens so that it projects a large image onto a screen, you would need to put the object between the focal point and 2 focal lengths away. The image would be inverted, but it will be real and projected onto a screen. Okay. You wouldn't want it outside 2 focal lengths because then the image itself would be smaller, and that would be very hard to see on the screen. Concave lens, we only have to go through one case because a concave lens diverges light, all right, very similar to a convex mirror. Okay, so it has this hourglass shape to it. Once again, we'll draw the 2 focal points where, the real focal point's on the front side of the lens, but we're also going to draw the symmetric one over here. If we place an object down anywhere, first light ray trace, horizontal. But remember, this diverges light, so this thing is going to refract upward, and it is going to refract upward at such an angle that if you were to backtrace this refracted beam, it would go through, all right, the focal point over here. Another light ray, if I send it towards the symmetric focal point on the other side, it will refract upward and go horizontally across. And lastly, if we send a light ray at the very center of the lens, it will continue straight through. all three light rays are spreading out. So if we backtrace the refracted beams, they will all meet at a location there. And this is why you see everything upright and smaller in a concave lens. The if I do I die formula still works with lenses. Image distances are negative when you have a virtual image. Now, those virtual images will appear on the same side of the lens, so you don't want to confuse yourself with what you did with mirrors. Okay? If the image is on the opposite side of the lens, you'll have a positive image distance because you have real images over there. Okay? Concave lenses, they diverge light, so they will have negative focal lengths. Right? Convex lenses converge light, so they will have positive focal lengths. Okay. You want to remember the focal length sign in terms of converging and diverging, not concave or convex, because for mirrors and lenses, they're flipped. Okay. Once again, 1 over f equals 1 over do plus 1 over di. Virtual images always have negative image distances. Real images are positive. Converging optics, right, versus diverging optics on your focal length, as already stated. And once again, object distances will always be positive because they are always placed at the front side of whatever lens or mirror you are using. Now, in reality, many things use multiple combinations of lenses. A refracting telescope, for instance, has a very large convex lens at the front, another smaller convex lens at the eyepiece. And what it does in that case, if we were to look inside the telescope, the light going through the large convex lens converges, right, and produces a small real image, right, because the object, the light from this planet, is very far away. But then that real image winds up being created inside the focal length of the eyepiece convex lens. And in that case, it acts as a magnifying glass, and you get a very large virtual image, which is what your eye sees. Okay, so many different optical devices use multiple mirrors and or lenses. All right, you can think of binoculars and telescopes and eyeglasses and microscopes all utilizing these ideas that we've covered. Okay. If you wanted to read up on lenses any further, there's some follow-up questions, right, in your textbook on page 511. You'll be working on a lens ray trace packet now. Until next time.